How to design a triangular oscillator circuit is explained in this video using a Astable Multivibrator. This is the 223rd video in the circuit design and analysis playlist. The plan is first quickly explain how the circuit works. How does it generate this triangular voltage at the output of the second op-amp, if this is op-amp 2 and this is op-amp 1? Then also, what is the formula for the frequency or period of this waveform that is generated? So what is the formula? And as a function of the value of the main components, there are 5 resistors R4, R5, R1, R2, R3, and then there is one main capacitor C, and then we have a Zener diode, and 4 typical diodes in a configuration that is a full wave rectifier here in the circuit. So we want to find the value of these resistors, and when we get to that, I'll just use the standard 1% tolerance resistors to find the proper value for these components. With that said, if you're interested to see more examples before I dive in, then there are more examples recently covered in the circuit, in the main engineering channel, and just recently I talked about the 4 transistor multiplier for audio signal, which is the black mirror gain cell here, as you can see, and then also recently the barometer instrumentation amplifier, log, anti-log amplifier, and 3-stage audio amplifier. And there are more examples if you are interested in seeing more examples. With that said, let me get back to the main example that I was about to cover. So here's the analysis. At the output of the circuit, we have, or we are saying it generates this triangular waveform. As you can see, this second op-amp, which I really recommend that we use op-amps from standard good op-amps from TI or analog devices that are dual supply. We need dual supply in this case, let's say plus minus 15 volt, not high. That's the level that we want to have these op-amps. So I make the assumption that a proper dual supply is applied, let's say plus minus 15 volt tops or plus minus 13 volt in this example. And then with that said, then we have this second op-amp configured here in the circuit as just a non-inverting amplifier. It's clear that if we have a Vx voltage here, this op-amp having a negative feedback will have also in a steady state Vx voltage on the negative terminal because of the virtual short of the input terminals of the op-amp. And then we have the amplification in which we can write V out, this V out is equal to just Vx times 1 plus R4, this R4, divided by R5, which is this resistor here. Okay, so this is the gain, and let's refer to this for the sake of ease of reference to it as just the gain of the this non-inverting amplifier. So in summary, I'm going to just say V out is equal to gain times Vx. So the voltage here multiplied by gain will give me V out. Now it's a linear relationship, of course, which I'm going to refer to it as relationship 1 or equation 1. If V out is triangular, then of course a smaller value of it, gain is more than 1, obviously, as you can see. So a smaller version of that is just showing up here. So there's a triangular, let's say, if I show it here. So there's a triangular waveform that is showing up here. Well, we have an RC circuit here. And that RC circuit is actually charging up capacitor in an exponential manner. So we know the way that the voltage of cap is charging up as a function of time when the cap is charging up is not linear. Is actually let me just show you here, is in an exponential fashion like this, getting to the final value if we let it to charge up. We don't want to use the charging process for RC for the whole range. We want to stick in the linear region. So in the linear region of the capacitor charging, if we can limit ourselves to that process, then maybe we can mimic the rise up in the triangular waveform. And then with the same manner, when the cap is discharging like this, then, let me just show it properly, then maybe then we can just stick with the linear region of discharging at the beginning of the exponential drop of the capacitor voltage so that we again mimic the downside or downturn of or drop in the triangular waveform. Okay, so the process is well known. We know that about 64 or 63% of charge up happens during the time that is 1 tau or time constant of the RC circuit. So time constant, which is tau, and we know for simple RC circuit it's just R times C. So if we want the to use absolutely the very close to linear relationship portion of the exponential rise or fall, then one good assumption is we need to make the assumption that the rise time or the fall time of the triangular waveform is less than, so rise time or fall time is half period. So half period should be less than or equal the time constant point multiplied by 0.1. So 1/10 of time constant. If we have half period, which is the rise time, for example, less than or equal 0.1 times constant, then we can say we have a linear, approximately linear rise and linear fall, which we need for triangular waveform. So that's one important condition that we have. We have to make sure that the RC time constant have the proper relationship with the period of the target triangular waveform. Now, okay, so what happens at this node, which a node I'm going to refer to it as VO1. So the main voltage is V out. This sort of a side voltage is VO1 at this node, which is basically this node here. So what happens is, if I make the assumption op-amp is properly biased and both op-amps are, as I said, proper op-amps from, say, TI or analog devices with dual supply use and with, let's say, near zero drift or very low drift, then we have safe paths to go. So let's make the assumption that with the dual supply connected, I'm going to make the assumption that the output of op-amp can go up to 13 volt and can go down up to negative 13 volt. That's one assumption I'm going to make. The Zener diode, let's make the assumption that when it turns on, in the reverse bias mode, the V Zener is equal to, in this design, is equal to 6.8 volt. So I'm using a standard 6.8 volt Zener diode. Okay, so imagine and make the assumption that input voltage for positive input terminal or non-inverting terminal of op-amp 1 is V plus, and input and voltage for negative or inverting input terminal is V negative. If we make the assumption that momentarily V positive is more than V negative, then of course as a result of that, given that open loop gain of this op-amp is very large, op-amp output would saturate to plus 13 volt, the max value. And as a result, it will send a current like this through this branch, through this diode, and down reverse bias of the Zener diode, and then through this diode down to ground. So we have basically this passage available. These two diodes will turn off. So they are not right now important in the analysis. And as a result, now the total voltage drop in the passage is, for these standard silicon diode, 0.7 volt, then 0.68 volt, and then we have another 0.7 volt here. So the voltage here is going to be equal to 0.7 and twice of that, because we have 2.7, two of that, and then we have 6.8 volt. So as a result, the final value is going to be 8.2 volt. Okay, so all I mean is, we have an 8.2 volt fixed value of voltage for VO1 at this node. So output of op-amp is clipped to 13, and VO1 is clipped via this full wave rectifier circuit. It's clipped to 8.2 volt. So let me use a different color here, so it clearly says 8.2 volt. Okay, so here we have an 8.2 volt that is basically charging up the capacitor via the RC chain. So again, going back to the concept that I just briefly mentioned here, we are trying to utilize the linear portion or near linear portion region of the exponential rise of the voltage of capacitor. So I can say that generally speaking, the voltage of this cap, as it's charging up, is equal to the final voltage, which is 8.2 volt, if we let it to get to the final voltage, plus the initial voltage. Well, if we take a look at the little circuit here, the second op amp is basically just a non-inverting simple amplifier. So via R4, R5, what happens is a smaller version of the output triangle. A triangular waveform appears here, as I discussed earlier, and then as a result, we have V out related to Vx. So relationship between Vx and V out is exactly V out equal to GVx, in which G is 1 plus R4 divided by R5. So as a result, and it's a larger than one gain. So we have this equation 1 that relates the Vx to V out, and Vx is a copy of V out, but in a smaller scale. So for example, if this output is, let's say, 1 volt, a desired, let's say, plan for the peak-to-peak voltage of the generated triangular waveform, then let's say this one is just a smaller version of that with a smaller peaks. So what I'm trying to say is when it's charging up, it charges up from a negative voltage to a positive voltage. So therefore, a starting point is a negative voltage, which is basically output divided by gain. So I'm going to write it here. The Vx, of course, the voltage at this node is V out divided by gain. So I'm going to say V out divided by gain of the non-inverting amplifier. And as a result of that, then minus the final voltage of the capacitor, e to the power negative t over tau or RC. So this is the general standard exponential equation for the charging up of a RC circuit for the cap. Now, because we made the assumption that the time during the charge up is much smaller than RC, then we can make the approximation that this e to the power minus t over RC is approximated by just simply 1 minus t, so roughly 1 minus t over RC. Okay, so I'm going to substitute that, and if you substitute that, you end up rewriting this equation in this form: V capacitor at any given time is equal to, any given time in the linear region is roughly equal to V out over G, and then we have, of course, from negative value of it. So it will be negative V out over G, and then we have plus V out over G, which is the gain of, again, G is here. So just to make sure that we don't lose the track of that, and then plus 8.2, plus because there is a negative and negative, and those two negative are canceled out by this negative in the formula of 1 minus t over RC. So if you simplify, we end up with this equation, t over RC. Okay, so in summary, if I clean it up, I will end up this equation. So VC at any time during the approximate linear region, plus I'm going to move this portion to the other side. So V out over gain is equal to, so that's now the left-hand side of equation. Right-hand side, I'm going to keep this portion, which means I have V out over G, and then plus 8.2, and then times T over RC. Okay, so the T is now, imagine when we are charging up at this node, we are going from, I'm going to move the cap here. So we are going from negative V out over G, basically negative Vx, to positive V out. So this peak is now positive Vx, so positive V out over G. So what I'm trying to say is the value of this Vc at time t, t being half period, is when the voltage of cap gets to, so in the half period time, the voltage of gap goes from the negative Vx to positive Vx. So I'm going to just basically say VCT is simply V out over G, and then we have another plus V out over G. So V out over G, so that means two of it, equal to V out over G plus 8.2, and then T is a half period, 0.5 period, divide by RC. Okay, so as just a standard value, let's use the value of 1 nanofarad for this capacitor. Just is a good value to select. We can go with 2 nanofarad, 5 nanofarad, or 10 nanofarad. But then in this example, let's use 1 nanofarad for the value of cap. And as a result, if the plant, so let's just summarize what we got. So now we have T equal to, so if we want to stick with T, I'm going to just write it that T is equal to basically the value of 2RC. So 2RC, and then we have 2. So I'm going to sum these as 2V out over G. And then denominator, we have these things is cross divide the left-hand side. So it becomes V out over G plus 8.2 volt. Okay, so that's one formula that I just obtained for the period. And if I just reshuffle that, I can rewrite it as the frequency. So obviously, because a frequency of this triangular waveform, so I'm going to write it here, the frequency is 1 over period. So if for example, if we want frequency to be, say, 10 kilohertz, then the period has to be obviously 0.1 millisecond, or basically 100 nanosecond, 100 microsecond. So, okay, so we are going back to here. If f is 1 over t, then I have the frequency of, say, the triangular waveform is equal to, now I just need to invert this, and we have 2 times 2, which means 4. So I will end up with V out over G, and then plus 8.2 divide by 4 RC, and then we have V out over G. And let's just divide everywhere by V out over G and finalize the formula. So I end up with computing that the frequency of the triangular waveform is just 1 plus 8.2 G over V out divide by 4RC. So this is one interesting formula that we got here. And of course, if I apply now the 1 nanofarad value of capacitor that I assume we have here for the cap, so this is 1 nanofarad. Then if, for example, the target voltage at the output of the circuit for the peak-to-peak value of the triangular waveform is plus 1 volt and negative 1 volt, then this V out is also 1 volt. And okay, so this V out is also 1 volt. Now, I have everything known here. The thing is, if the frequency is 10 kilohertz, for example, the target is 10 kilohertz, so 10,000 hertz, then the question is, what is the gain for basically what is 1 plus R4 divided by R5 in the circuit as gain? So I said the value here is what is referred to as gain. So what is the gain of this second stage? And then also, what is the value of this R, which basically is R1? So I kept it as R, but it's just R1. So obviously it's R1. All right, then I'm going to go back to what we found here in the equation, say number 2. So in the equation number 2, we found that half of period should be less than or equal 0.1 tau. Okay, so I'm going to rewrite it here. So again, equation 2 states that half the period should be less than or equal 0.1 tau, and tau is RC. So that's an important outcome. If t is 100 microsecond and if c is 1 nanofarad, then we have a specific requirement for the value of resistor. So if I just shuffle things around here, then R becomes more than or equal, then we have 5 T over C, which means if we compute this value, we end up with finding the value of R. So T is, as I said, is 100 microsecond, and C is 1 nanofarad. So if we just put in place, we end up with, for example, value of R in the circuit should be more than or equal 500, about say 30 or 20 kilo ohms. So one good choice for the value of resistor, so this is R1. Value of resistor R1 is going to be 536 kilo ohm. And that's a very good choice, because if we look at the value of resistors available for tolerance of 1%, which is something that we really desire, we can see that 536 kilo ohm is a standard value for resistors. So 536 kilo ohm is something that we would like to have in this case. So 530 kilo ohm is a good choice. Now, with that said, if we have 530 kilo ohm, we can go back to this equation number 3 that we found. And equation number 3, if we supply all the values and now we have R1 selected as 530, we end up with, so I'm going to say with the value of R1 equal to 536 kilo ohm, and R1 again in the circuit is this resistor and also this resistor for the symmetricity, so that we have from both sides of op amp toward its input terminal, we are observing similar resistance for better performance. So therefore, we have 536 kilo ohm, and then using equation 3 that says frequency is 1 plus 8.2 gain divide by output voltage, divide by 4 times R1C. If we do so, then of course substituting F with 10 kilohertz and substituting V out as 1 volt, as I said, it means we are targeting plus minus 1 volt peak to peak for the output triangular waveform, and also substituting R1 536 kilo ohm and C 1 nanofarad, then we end up computing the value of gain, and the gain turns out to be 2.5. And the gain is, if I go back to show you the formula for gain for the second stage for the non-inverting amplifier, is 1 plus R4 divided by R5, as you can see here for the gain. So with that said, therefore, I can just go here and say, okay, this is equal to 1 plus R4 over R5. So the conclusion is, as a result, R4 over R5 has to be 1.5. So as one good choice would be if we go with R4, say 15 kilo ohm, and if we go R5, say 1 kilo ohm, 10 kilo ohm. So here, therefore, as a result, I'm going to write it on the circuit. So we have the value of this guy as an example here, 15 kilo ohm, and the value of R5 is 10 kilo ohm. This way, what happens is, because the gain is 2.5, so this G, as I showed you, turn out to be 2.5 as we computed, then it means if we have plus minus 1 volt at the output of a circuit for this amplifier, plus minus 1 volt, then it means that the smaller scale, basically Vx that you can see here, Let me just make sure that I'm not. Okay, so this negative Vx for the negative side is going to be 2.5 less than this negative one, which means negative 0.4 volt. And the positive Vx on the positive side, so this one is positive Vx, which is 0.4 volt. Okay, so that means as V out is going 8.2 volt, then the cap is charging from negative 0.4 volt to plus 4 volt so that we get the rise time for half period of the triangular waveform at the output of the circuit. But what happens is we need to set the reference voltage at the positive or non-inverting input terminal for op-amp 1 to 0.4 volt now. So the reason for that is it's, as I said, we are using a stable multivibrator, which means that we are just gonna set this voltage at 0.4 the moment this capacitor voltage reaches 0.4 volt, then this assumption will go away and actually it reverses. Reverses meaning that the voltage of positive terminal for op-amp 1 becomes less than voltage of negative terminal. And as a result of that, everything will switch. The output will go from 13, the output of the op-amp will go from 13 down to negative 13. So I'm going to just rewrite it here. Suddenly, instead of 13, it becomes negative 13. And then as a result, the direction of current going to change. So used to be this way, but now it will change and it becomes this way in this full wave rectifier. So now we have same situation, but from ground down, we have plus minus 0.7. And then again, we have via the Zener, we have plus minus V Zener, which is the 6.8 volt drop. And then we have plus minus 0.7 across this diode. And this time, these two diodes are off. So as a result, we have, therefore, the negative 8.2 volt here. So instead of positive, now we have negative drop. There you go. So we have negative 8.2 volt here. And therefore what happens is this chain, let me change the color so that it's clear. This chain, this RC chain, start to discharge the capacitor. So now the cap is going to be discharged. So from whatever voltage it got to, I'm gonna show here. So the cap, as I said, we sort of use the, we focus on the linear portion of the rise, and then we got to this point. And then at this point, we are now discharging the cap again using exponential drop, but then sticking with the linear portion of exponential drop. And remember, this is the voltage of capacitor, and this is time. So we have now using this region, and after that we go back to linear region, and this is the way we generate the triangular waveform at the output of the circuit. Okay, so with the same argument, the whole thing that I said here is going to be repeated, but here's the thing. We want at least 1 milliamp, even more sometimes, depending on data sheet of the Zener diode, to pass through the Zener diode and the circuit so that the diodes are operating properly. So one requirement is R3 need to be set so that at least 1 milliamp is going here. Okay, so think about it. We have 13 volt or negative 13 volt on one side, and we have 8.2 or negative 8.2 on the other side. So basically the current that passes through R3 is simply 13 minus 8.2. So that current is either this way or that way. I don't care about direction, I just care about the value. So divide by R3, this has to be greater or equal 1 milliamp. So with that said, I even prefer it to be 2 milliamp or 4 milliamp, depending on what is the Zener diode requirement, but then that would set a minimum value for R3. In this case, if you compute that, you end up with R3. So if you just process this, you end up with R3 should be at most 4.8 kOhm. So let's say 4.7 kOhm. So I would prefer to set R3 at most 4.7, but maybe a good value for R3 is say 2 kilo ohm or 2.7 kilo ohm, for example, to just make sure that we have 2 milliamp current flowing. And remember, we found R1 before, so I'm going to write the value of R1 here as well. We found in this example R1 is 536 kilo ohm, 1% tolerance. The same thing with this R1 here. It has to be 536 kilo ohm. Let me change the, this is too busy. So this one is also 536 kilo ohm in this example. R3, let's say we just found R3 to be, so we just found the R3 to be, say 2.2 kilo ohm as an example, or a max 4.7 kilo ohm. Now, what is the value of R2? Remember, we said we want this V positive to be equal to 0.4 volt as a reference, right, for the astable multivibrator. So now we have a voltage divide between R1 and R2 from the VO1 of 8.2 or negative 8.2, and we know that the positive terminal should be 0.4. So I'm going to write it here as the last step. As the last step, I'm going to just say V positive op amp 1 is equal to 0.4 volt, and it's simply a voltage divide. So the value of resistor is, as you can see here, is R2. So there's a simple voltage divide, R2 divided by, so R2 divided by R2 plus R1 give us what we want. So I am going to say R2 divided by R1 plus R2 times the voltage is 8.2 volt at that's VO1. So recall that at this VO1, we have either 8.2 or negative 8.2, depending on rise or fall time. So basically, as I showed, VO1 is a rectangular, just square wave pulse, and that is a byproduct of the circuit. So circuit generates both a square and triangular waveform. And then we have R2, R1 is already computed. That's 536 kilo ohm. So 536 kilo ohm is R1. And then as a result, we can just compute the value of, the R2 from this analysis. And if you compute that, we can find the value of R2. I mean, it will be a quick calculation here. So it will be say, let me just quickly flip it so that we can do a quick calculation. So it becomes R1 divided by R2 plus 1 is equal to 8.2 divided by 0.4. So we end up basically computing, let me just quickly do that. So it will be 8.2 divided by 0.4, which is equal to 20.5. And then from this calculation, we get R1 divided by R2 should be equal to 19.5. Given that, so basically as a result, we get that R2 should be equal to the 536 kilo ohm R1. So 536 kilo ohm R1 divided by 19.5. So if we compute that, 536 divided by 19.5 is 27, so 27.49 kilo ohm. And one good news is, again, I'm glad I have this table here. So this table of a standard tolerance, again, if you go with 1% tolerance for this design, you can see that something close to 27.49. So 27.49 is here. And we are lucky. So we have it, actually. So if we go with 1% E96 for the resistor, then we have 27.4 as the standard value. So I'm going to just make the approximation that therefore R2 is 27.4. That's the value of R2. Okay, so I'm going to write it here then. So here the value of R2 is going to be, if this let me, then I'm going to write it here. The value of R2 is going to be 27.4 kilo ohm, and it will be similar to other resistor. It should be 1% tolerance. So all resistors in this circuit, 1% tolerance or even better. Okay, so R2 27.4, R1 536 kilo ohm, and then C is 1 nanofarad as we discussed, R4 15 kilo ohm, R5 10 kilo ohm, and the Zener diode is 6.8 volts. So with that said, we are able to then generate the plus minus 1 volt square wave and also plus minus 8.2 volt. So negative 8.2 roughly and positive 8.2, the square wave on top and triangular waveform plus minus 1 volt down in the main output of the circuit. If you want a larger, let's say swing, or let's say peak to peak for the triangular waveform at the output of the circuit, then we need to increase the gain, which means we need to increase the value of R4 so that we get more gain or G from this second non-inverting amplifier at the output of the circuit. I hope this example is helpful in terms of understanding how we can design a triangular and a square wave oscillator using a stable multivibrator. Thanks for watching.